All right, welcome back to part 2 of conditional probability and independent events. We just left off talking about how to test for independence, looking at those three properties above there. If the probability of A given B is equal to the probability of A and B are independent. If the probability of B given A is equal to the probability of B, A and B are independent. And if the probability of A and B is equal to the product of the probabilities of A and B, events are independent. If any of these are not true, the two events are not independent. Okay, and again, that just means that some relationship exists between these particular categories of events. Okay, but let's take a look at some examples here. In the first one, it says, to illustrate the calculations involved in evaluating a diagnostic test, we consider the case of tuberculosis, an infectious disease that typically attacks lung tissue. Before 1998, culturing was the standard method for diagnosing TB. This method always resulted in a correct diagnosis, but it took 10 to 15 days to produce a test result. In 1998, investigators evaluated a DNA technique that turned out to be much faster. The DNA technique for detecting tuberculosis was evaluated by comparing results from this new test, to the existing gold standard, which is always correct. And the table below shows the results for 207 patients exhibiting symptoms. So there were 207 patients that had symptoms of TB. They took both tests. They took the new test. That's what's on in the rows here. Okay. And they took the old standard test, which is 100% accurate. And that's what the columns are here. Okay. So, as we look at the data, there were 14 people who both tested positive in the new test and actually had tuberculosis. There was nobody who tested positive with the new test and did not have tuberculosis. Okay, so that's good. So what does that mean? It means nobody tested positive and actually didn't have the disease. Okay. So what would we call that? A false negative, perhaps, or a false positive? Let's take a look at the other two numbers. The 12, DNA negative test indication. So the new test came back negative, but the person actually had tuberculosis. Okay, so that's not such a good number. The new test came back negative, but they actually had it. That's a false negative. Okay, that's a false negative. And that kind of thing happens, all right? And then if we look at the 181 in the bottom right corner, the DNA test, the new test came back negative, and the standard test showed that they did not have tuberculosis. So that's a true negative, and that's good. So for the majority of the tests, we get accurate results. When they had it, the test tested positive. When they didn't have it, the new test tested negative. All right, but we do have those 12 false negatives, okay? In any event, point of this example is just to get a sense of, taking the data in a two-way table and converting it into what are known as joint probabilities. And it's actually very simple to do. To take the table on top and get these decimal values down below, all we do are take all these numbers, every single one of these numbers, these 9 numbers, and we divide by the entire sample size, 207. All right, so if we take all those numbers, 14 divided by 207, 0 divided by 207, 14 divided by 207, 12, 181, 193, so on and so forth, all those numbers, we divide all those by 207 and we get, what's called the joint probability table, okay? And that just shows, instead of the frequencies, the relative frequencies, okay? It's the percentage of the total that exhibit these traits. For example, 0.0676, a little under 7% of this entire population both tested positive with the new test and had tuberculosis, all right? 87% of the population both tested negative with the new test and did not have tuberculosis. Just over 93% of the population in total tested negative. Okay, the 0.1256 down here. A little more than 12.5% had tuberculosis. So you get the totals there, okay? So again, this is just called the joint distribution table. It's very simple. You take all the original numbers and divide by your entire sample size, which in this case was 207. Okay, a quick look at the table indicates that the DNA technique seems to be working in a manner consistent with what we expect from a diagnostic test. Samples that tested positive with the technique agreed with the standard test in every case. Samples that tested negative were generally in agreement with the standard test, but the table also indicates some false negatives. Now think about a randomly selected individual who is tested for tuberculosis. Define the following events. T is the event that the individual has tuberculosis. N is the event that the DNA test is negative. Then the probability of T given N denotes the probability of the event T given that event N has occurred. We calculate this probability as follows. Well, it's the probability of T given N. That would be the probability they have tuberculosis given the new test came back negative. Well, by the formula, that's going to be then the probability they have tuberculosis and the DNA test came back negative divided by the probability the DNA test came back negative. And now both of these numbers, if we know where to look, can be found up in that table. Okay, the probability they have tuberculosis and the test came back negative, let's see, that's where they overlap right there. DNA test negative and has tuberculosis. So there's that joint probability, the 0.0580. In terms of the denominator, we want the overall probability that the test came back negative. So if we look at the DNA test coming back negative, the overall probability of that is that 0.9324. And that's where those numbers come from, okay? So, to make a long example short, so to speak, the whole point of this is, again, with a two-way table, we can convert cells into joint probabilities, and then we can use these tables to relatively easily, as long as we know where to look, come up with these conditional probabilities or even and probabilities or all sorts of stuff, okay? So let's take a look at the next example, and we'll put one together ourselves. All right. The test results of 88 students is recorded in the two-way table below. So we have one category is male versus female, the other category are grades, okay? And we can see all the data there, and grand total 88 students. Okay, and from this we're going to randomly select one student. First up though, find the joint probabilities by converting the data into the proportions, okay? So that's just what we did up above. We're going to take each of these original numbers, those 12 numbers, and we're going to divide them all by 88. All right, and I'll try to round to 3 places here. So let's see, 15. I'm going to work, from the top down. So I'm going to go across this row, then I'll work down to the next one, okay? So I'm going to do 15 divided by 88. That's about 0.170. I'm going to do 20 divided by 88, 0.227. 13 divided by 0.148. And I would actually do 48 divided by 88 as opposed to adding these 3 numbers up to get the total, only because we're rounding and it'll be more accurate. Okay, so I'm doing 48 divided by, and I'm getting 0.545. Okay, now going through the female row, 12 over 88, 0.136, 19 over 0.216, 9 over 88, 0.102, and 40 over 88, 0.455. Okay, and now going through the totals, row 27 over 88, 0.307, which is what it rounds closer to. If you actually added those, you get 0.306. All right, so that's what I'm talking about. Better to divide than add in terms of these totals. So I'm going to do 39 divided by 88, 0.443, And 22 over 88 is 0.25 on the nose, 0.250, I'll write that as. Okay, so that's all it is. Take the time to divide through. And now let's go through and practice some probability questions, okay? So in part B, what's the probability we randomly select someone who got a B given it's a male? All right, so we know that we selected a male. Of the males, what percentage of them got Bs? Well, here's the formula. It's going to be the probability they got a B and they're male divided by the probability they're male. There's the formula. And now what we do is we look in the table for these values. We're looking where B and M overlap. B and M, that's the 0.227. And now we're going to divide by the probability of M. So the total probability of M, 0.545. And let's see what we get. We get about 0.417. All right, so a little less than a 42% chance that we randomly select someone who earned a B given they're male. Another way to think of this is of the males, 41.7% of them earned Bs. Okay, that's what that represents. All right, whoops. Okay, part C. Now, notice we flipped the condition around. Probability, it's a male given they got a B. So here we're basically saying, look, of the students who earned a B, what percentage of them are male? What's the probability we randomly select a male from all the students who earned Bs? Well, again, running through the formula, it's going to be the probability of M and B, but this time divided by the probability of B. Let's find the value for M and B. Well, it's exactly the same as it was above. M and B overlap, and that's 0.227. But now the total probability we randomly select someone who got a B is that 0.443 at the bottom of the B column. And that ends up being about 0.512 here. So a little more than a 50% chance that we randomly select a male given they got a B. Or another way to think of it is of the students who earned Bs, 51% of them were male. Okay? All right, next up, the probability we randomly select someone who earned an A given they're female. So that's going to be the probability they got an A and are female divided by the probability they're female. So where do A and F overlap or meet up? 0.136 up in the table. And the total percentage of females, 0.455. Overall probability, just about 0.299. So just under 30% of the females earned A's. And if we flip that around, what percentage of students are female that earned A's? Okay, or what's the probability we select a female from among all the students who earned an A? So again, probability of F and A divided by the probability of A this time. F and A still the same, 0.136, but probability of A, total percentage who earned A is 0.307. And that comes out to about 0.443. Okay, so just over 44% of the students who got A's were female. Okay, so a little practice with conditional probability here. Now, let's determine, are being female and getting an A independent events for this group? So again, this is not a common sense approach to independence. The answer is not no. Being a female and getting an A have nothing to do with each other. They're independent. That's not what we mean here. We're talking in a mathematical sense, okay? So what we're going to do is we're going to run the test for independence. And, look, we're asking, are being a female and getting an A independent events? Well, if they are, any of those three properties at the very beginning of this lesson and at the end of the last one for those tests of independence are going to hold true. I'm going to go through each one here, okay? But you only have to show one. You don't have to do it all three ways. So look, if events are independent, if F for female and event getting an A are independent, then, okay, then, look, one thing we could try to show is, does the probability of A given F just equal the probability of A? All right, let's look at that. Now, up in part D, we computed the probability of A given F. That ended up being 0.299. The question is that the same as the probability of event A occurring on its own? Well, if we go back up to the table and look at the bottom of the A column, total percentage who got A's was 0.307. Are those values equal? Of course not. Since they are not equal, events being female and getting an A are not independent, okay? Events being a female and getting an A are not independent. It just means that within this group of 88 students, there's some relationship between getting an A and being a female. That's all that means, okay? Look, another thing we could have shown was the flip of that. We could have shown, does the probability of F given A equal the probability of F on its own? Well, okay, up in part E, we already computed the probability of F given A. That was 0.443. Does that equal the probability of randomly selecting a female? Well, if we look at that, you know, the number's close. The total percentage of females, 0.455. But again, they're not equal, so same conclusion. And if the first one wasn't equal, the second one's not going to be equal. And the third one that I'm going to do right now isn't going to be equal as well. It's not going to work for one test and not the others. I'm just showing you that we could have used any of these to show the events are not independent here. The third test would be to say that the probability of being a female and getting an A is equal to the product of being a female times the product of getting an A. Well, probability of F and A is actually right up in the table. F and A is that 0.136 where they overlap. And the question is, does that equal the probability of F times the probability of A? Probability of F was 0.455. Probability of A was 0.307. So let's see if we punch this in. Does that product equal what we're after? And I'm getting, it's close, 0.139685, but close doesn't cut it. They're not equal, same end result, events are not independent. Okay, so that's the idea for tests for independence in this mathematical sense. You can run through any of the three of these conditions. If they're equal, events are independent. If they're not equal, events are not. Okay, and another couple examples here, and hopefully you get the gist of this stuff. The paper, Predictors of Complementary Therapy Use Among Asthma Patients, Results of a Primary Care Survey, included the accompanying table. The table summarizes the responses given by 1,077 asthma patients to two questions. Do conventional asthma medications usually help your asthma symptoms? Do you use complementary therapies such as herbs, acupuncture, aromatherapy in the treatment of your asthma? And here are the results, okay? Now, they didn't total things up for us, but let's see what we've got. 816 participants don't use the complementary therapies and say that conventional medicines help. 103 participants do not use complementary therapies and say conventional medicines usually do not help. Conventional medicines usually help and does use complementary therapies is 131 participants, and the remaining 27 do use the complementary therapies but don't find the conventional medicines helpful. Okay, let's total these up pretty quickly here. If I add across the first row, I'm getting 947 patients who typically use the conventional medicines for help. If I add 103 and 27, that's 130 who say the conventional medicines don't help. Adding those up, we do indeed get total sample size of 1077. Adding down, looks like 919 do not use complementary therapies. and 158 do. And I'm just going to double check that those add up to 1077, and they do. Okay, so there's the table with the frequencies. In part A, construct a joint probability table by dividing the count in each cell by the sample size, 1077. Okay, so same thing we just did in the previous one. I don't need a calculator for this one. Again, we'll go 3 places here. So take a moment to do that. And notice my notation that I'm using here, by the way. I'm using CT for complementary therapies. I'm using CT with the line above it to indicate that they don't use it. That was a notation that we talked about in the previous lesson, meaning not. Okay, so they don't use complementary therapies. I'm using CH for conventional help, and then I'm using not CH for conventional do not help. Okay, so that's what that notation represents, by the way. Okay, going through, continuing to divide. All right, so, check your data with mine. Hopefully we're all good here. Let's take a look. Part B. All right, so that was part A. We, again, just practice dividing. Shouldn't be too big of a deal. Part B, the joint probability in the upper left cell of the table from part A is 816 over 1077 equal 0.758. There it is. This represents the probability of conventional medications usually help and does not use complementary therapies. Interpret the other 3 probabilities in the joint probability table. Okay, so 0.122. What does that represent? Well, that's the probability or the percentage of people who say complementary medications help and use complementary therapies. Okay, those are the percentages for the intersections or the ands. This 0.096 is the percentage of people, or if we were to randomly select a person, the probability that we select somebody who says the conventional medicines don't help and they don't use complementary therapies. And the 0.025, right, basically 2.5% of this population say that they do use complementary therapies and conventional medicines do not help. Okay, so again, those are the ands. Those are all the ands, and those are called the joints. These totals, again, are called the marginals. Okay, the 0.879 is just the total percentage of people who find conventional medications helpful. The 0.121 is the percentage who find conventional medicines not helpful. The 0.853 is the total percentage of people who do not use complementary therapies, and the 0.147 is the total percentage of people who do use complementary therapies. Okay, so again, just with terminology, the joints are the highlighted ones in the middle, and the totals are your marginals. Okay, part C. Are the events CH, the event that the selected participant reports that conventional medications usually help, and CT, the event that the selected participant reports using complementary therapies, independent events. So again, we could go through it a bunch of different ways, but I'm going to look at it this way. I'm going to say, for part C, let's see, does the probability of CH and CT, does that equal the probability of CH times the probability of CT? Let's go through this way. So one of the highlighted numbers is the probability of CH and CT. Which one's that? Well, that's the 0.122 in pink up there. Okay. Now, let's look at these total probabilities. The total probability of CH. So there's the CH row, the total probability 0.879 times the probability if they use complementary therapy. So that total probability 0.147. So again, close is not good enough. The question is, do these things end up being equal? Well, let's punch this product in on the right. And I'm getting about 0.129213. So while they're close, they're most certainly not equal. So no, events CH and CT are not independent. Here. Okay? All right, and then last page, the article SUVs score low in new federal rollover ratings, gave information on death rates for various kinds of accidents by vehicle type for accidents reported to the police. Suppose that we randomly select an accident reported to the police and consider the following events. R is the event that the selected accident is a single vehicle rollover. F is the event that the selected accident is a frontal collision. D is the event that the selected accident results in death. Information in the article indicates that the following probability estimates are reasonable. The probability of R is 0.06. So the probability it was a rollover, 0.06. Okay, the probability it was a frontal collision, 0.6, so 60%. The probability of R given D, 30%. The probability of F given D, 54%. In other words, well, in part A and B, we'll interpret these things. So interpret the value of probability of R given D. That's the probability or percentage of accidents that were rollovers given death occurred. Okay, that's a conditional probability. Probability of R given D, or the percentage of R given D. The percentage of rollovers that resulted in death. Another way to say it is it's the percentage of deadly accidents that were rollovers. Okay, the percentage of deadly accidents that were rollovers. That's another way to put it. Okay, for part B, interpret the value of the probability of F given R. Okay, F given D, excuse me. So that's the percentage of accidents that were frontal end collisions given death occurred, or it's the percentage, we actually know the percentage, by the way, 54% of deadly accidents were frontal collisions. Okay, and actually for the last one, that was what, 30%? So I could be a little more specific up here and say, look, 30% of the deadly accidents were rollovers, 54% of the deadly accidents were frontal collisions. Of the deadly accidents, this percentage were due to rollovers. Of the deadly accidents, this percentage were due to frontal collisions. Okay, so that's what those conditional probabilities represent. Our events are indeed independent. Well, let's see. If R and D are independent, again, we have different ways to test than either the probability of R given D would equal the probability of R, or the probability of D given R would equal the probability of D, or the probability of R and D would equal the probability of R times the probability of D. All right, now let's look at what information we've been given up here. Do we have the probability of R given D? Yes, we do. Do we have the probability of R? Yes, we do. So we can look at that comparison. And actually, we don't have any of this other information. So, you got to know all three ways to test for independence. And then the way you test is sometimes open to your choice, like in those problems above with the two-way tables. But in a case like this, we're really forced to test in this first way because of the information we've been given. Okay, so we're going to look and see, are these two probabilities equal? Well, there's nothing to really compute. We have both those numbers. That's 30%, which certainly doesn't equal 6%. So no, these events are not independent. There's a relationship between whether it was a deadly accident and a rollover, and that's basically the gist here. Okay, part D. Is the probability of F and D equal to the probability of F times the probability of D? Well, this is just another way of asking, are events F and D independent? Right? If events are independent, then this particular and formula would uphold. All right, so it's kind of like really what they're asking is, are these events independent? All right, so look, let's see, F and D. F and D. Well, so again, if they're independent, another thing we could look at is the probability of F given D the same as the probability of F then. Okay, and that's the additional information that we had up there. And 54% does not equal to 60%, which are the numbers they gave us. And so no, these events are not independent either. And in part E, is F equal to R with a superscript of C? So again, that notation we saw back in one of the first lessons, that means that's just the same as not R. So they're basically saying is set F, the frontal collision's the same as not R. You can write it like this if you prefer, okay, the not R. Okay, but that's what that symbol means. Are those the same groups of people? Well, look, if F is equal to that, if those are the same sets, then the probabilities of these things would be equal. The probability it was a frontal collision was 60%. What's the probability it's not a rollover? Well, the probability it is a rollover is 6%. The probability it's not a rollover then is what? The remaining 94%. And these are very different. So no, frontal collisions and not being a rollover are not necessarily the same thing. Just because it wasn't a rollover doesn't mean it was a frontal collision in this sense. Could have been any other type of accident, okay? But in any event, try to get the formulas down and the test for independence. And if you have questions, shoot me an email. See you, folks.